Hello everyone, my name is Michael and we're going to take a look at some ransomware. Now today's sample, I'd like to take a look at seeing if we can crack the Keygen. So let's start out by taking a look at what compiled this, and we'll see it's actually a Borland Delphi sample. And just checking the entropy, it's not packed. So we're actually going to be dealing with a Delphi written malware. So let's go ahead and take a look in IDA, the decompiler, and we'll see that for whatever reason it didn't really make a nice graph of the starting point, but we can already see some strings of this is actually going to end up being some garbage that they put in the ransom note. So this kind of identifies what ransomware this is, but let's take a look at the imports here. So there's actually a couple functions that will catch my eye. We have a get tick count and a query performance counter. Now these two functions are usually kind of the backbone of the standard random functions used by the C library. So let's take a look at where this is referenced. And we'll see, yep, they're used in the same function. So it looks like we're gonna call this function. This is actually like a structure, you have to pass it. And if that fails, then we fall back to get tick count. So this actually, just from experience, this is actually, I believe, the function srand. If you're familiar with C, this is how you kind of generate random numbers. So we can go ahead and rename this to srand. Because by standard you usually would call it with srand and pass it the current time, which is what get tick count basically ends up being. So let's go ahead and see where this is called from. Now, if we kind of look at the logic of this, we're calling srand, or what we perceive as being basically srand, and we're passing in a character set here. We can see the full string of some random characters. We're iterating over a loop of probably ESI is usually kind of your I variable. And we're calling some functions and then returning down here. So this already kind of looks like it might be some type of a keygen. So let's take a look into, so we've got the srand. You can kind of dig through some of these that end up being rabbit holes of functions, and sometimes I'll look through there, but if we kind of continue through, there's some more rabbit holes. Let's take a look at, not that function, but let's take a look at this function. And here, we're actually doing a multiplication by a number here, incrementing, and this actually is a random number generator. This is actually a what's called a Linear Congruential Generator, and this is also known as an LCG. It's a particular algorithm that's actually very common for a lot of random number generators. And if we actually take a look through here, blah 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 math, there's a table with some values here that will be interesting to see, but we can scroll through all the theory. We can look at a simple Python implementation of this algorithm. So if we kind of compare this, I'm going to flip back and forth here. So we're going to iterate, we're going to have a seed variable that we pass, and then we overwrite it each time. And we're going to take an A times our seed and then add something. And we'll see here, this actually looks like it's probably going to be our seed variable. We're multiplying it by this number, which I can change that with the H key into decimal. And then increment is actually just the same as a +1. So we already know that this is Delphi. Let's take a look at our table up here. And let's see, Delphi uses these constants, multiplier of this number, increment this number, and yep, that's our same number here. So if we actually look further on this Wikipedia page, there's actually a nice implementation of, here's a Delphi compatible example, and we can kind of confirm that they're using. This is basically the function we're in right now. We have our seed times this constant plus 1, store it back in seed, and then return it. So we can go ahead and rename this as rand. Let's go back here. So at this point, we probably have a pretty good idea about how this keygen works, knowing that it's Delphi, and knowing that this is basically the source code of it. So let's go ahead and take a look in a debugger here. So actually, I want to, let's go ahead and rename this as our keygen. And we are at address 414.800. Let's go ahead and set a breakpoint. BP 414.800. All right, so I'm at the enter point right now. Let's go ahead and jump. All right, so we're in our function now. Let's just kind of watch what happens here. So pushing onto the stack, doing some stuff. Let's see, what's this first call going to be? This first call is going to be our srand. And let's jump into that. And yep, here we go. Query performance counter. Test of it failed, which EAX is 1, so it did not fail. So we're going to go to here. We're going to push some type of variable into EAX. Let's take a look at that. Okay. And then, all right, so we have a value here. Now, since we know that this is basically more or less random, or rand, this is actually the current time, pretty much. It might be a tick count, depends on how this is implemented. So we can go ahead and we can just keep an eye on that number there. So we go through here, and we're back at our main keygen function here. So we see here's our big, here's our string. That is our character set. Now let's go ahead and jump through here. And sometimes the first time I don't really pay attention to exactly what these steps are, but I kind of watch what these strings that are popping up are. So we've entered a loop here. We just saw a string flash by. Let's kind of step through here. We have a jump condition. We're going to jump back to the start. And okay, we saw some strings flashing by there. Oh, we have an LM. Looks like our loop condition is F, which is 15 in decimal. So we're going to do this loop 15 times. We can slowly see our key being built. LMCES, blah, blah, blah. Let's go ahead and skip to the end. And all right, here's our key. So if we take a look at that, here is our full, whoops, here's our full key. And we'll see it's 15 characters, F. So let's do a little trick here to make things a little easier for ourselves in analyzing this keygen. I'm going to restart the executable, jump to the entry point. Let's go back to our keygen function here. And let's step into that srand. So we're going to step over, and we're going to move something into EAX, which is actually, this is, if I'm reading this correctly, this is a result from query performance counter. We pushed some memory into it. And then it returns EAX just saying whether it succeeded or not. But then it actually puts into our memory that we gave it the result. So I'm going to do that. Then we have this variable here that we want to return and create our seed. So actually, if I go back to the disassembler here, we can go ahead and rename this. This is our seed. And we can actually also confirm by doing a cross-reference. We see it's called in srand, and it's also called in our rand. And here's where we're using that seed and moving our result from the multiplication in the increment back into the seed before we return it. So let's go ahead and do a little trick here. I'm going to hit space on my keyboard, and I'm going to overwrite this command. Instead of taking the return of EAX, I'm going to hit keep size, fill with nops. Let's go ahead and overwrite this command, and we are going to let's go ahead and just nop it. So we're going to overwrite this function. EAX already should be the variable that we have here should already be initialized to 0, and we're going to keep it that way. So let's take a look at our pushing through here, and let's go ahead and jump to our final thing here. So we have this string. So this is a string that's going to be created if we give it a seed of 0. So to keep this, I'm going to go to File, Patch File. We'll see here's all those commands that I nopped, replaced with nothing pretty much. We're going to go ahead and patch file. I'm going to call this patched. Not valid. Okay, I got to give it an extension, I guess. That bin. All right, so that is patched. Now let's go ahead and stop this executable because we want to now work with our patched version. Now I'm going to have to set up the breakpoints again. Let's see, this was called from here. Let's jump back into our keygen. Okay, 41480. BP 414800. Okay, let's entry point keygen. Let's see. We want to go to, let's go to the return. Execute to return, and yep, still worked. We can go ahead and set a breakpoint there one more time just to make sure that it's still not selecting its own seed. And yep, we got the same key. So this is very helpful so that we can kind of troubleshoot our own keygen for it. So with this knowledge, we know it's a LCG, and we know what its constants are. Let's go ahead and make kind of a proof of concept, not decryptor, but keygen here. Let's see if we can recreate this key. So let's call this keygen.py. We're going to do this in Python real quick. Now, I'm not cool enough to do this live while I'm editing this, so I'm going to reference keygen I already wrote on my other screen. Let's do some imports. So first off, we need to know the char set. These are going to be the characters that we randomly selected. Let's go to strings. All right, let's select this right here. So this is the character set that we are randomly selecting from. If I could put it inside the quotes. Now, the heart of our keygen is the Lcg algorithm. And as I pointed out, we already have that in Python. Let's go ahead and copy that. So we have a keygen, so we just need to know the modulus and then the constants A and C, and then pass it our seed each time that we use it. So let's go ahead and make a little helper function here. Call it rand. We're going to pass it the seed, and it's going to know all of our constants already. So let's return, this is a generator. If you haven't seen the yield command before, each time this function's called, it yields the next one in line pretty much. So it's a memory efficient way of doing a for loop kind of. So let's do LCG. Now the modulus is going to come from our table here. Let's see, we're at Delphi. Modulus is 2 to the power of 32. So in Python we do that with 2 asterisks. 2 to the power of 32. Now we need our multiplier is A. Oops, Control V. Then we have our incrementer is 1. And then let's pass it our seed. All right, so now we need to make a keygen function. We're gonna, by default, pass it the seed of 0, and we can pass it a length. So as we saw in our in the assembly here, let's go back. I kind of briefed over it, but if we look at the keygen, it's actually called twice, and it looks like the first time it's called with a 15. F is 15 in hex. And then another time we generate another random 5 characters off the same keygen. Something to keep in mind is that each time this keygen is called, srand is reseeded. So the numbers are started with another, normally would be started with like the next tick count. So let's go ahead and set up some variables. We have our key. We're going to need a loop iteration. Let's go ahead and cache the length of the char set. So we're going to use that a little bit. And let's go ahead and use our generator function here. So for c in rand of our seed. We're going to iterate over that. Now, since we're iterating over the generator, we still need to have a break condition. So we're going to do until we hit the length. I'm going to break. Oops. Used to doing semicolons. We're going to add part of our char set. Now, let's take a look back at our code here. Now, there's something to notice here. So we have the regular random. This is going to call the im function, which is this. This is our LCG. I'm not sure why it's called im, but I actually wouldn't worry about this. This is scientific notation with a -10, so I'm not sure if this is just some precision point thing, but we'll see if we have a certain range that we want to do. So this would be our max value. We want to take the result of the LCG times our range and do a right shift by 32 bytes. So, a quick note about this is these are longs, so these are 64-bit integers. I did run into a little problem with this translating it to like C#. I forgot to use 64-bit integers and would produce the wrong numbers, but Python takes care of that for us. So what we need to do is take our char set. So we have our LCG value. We're going to multiply it by the length of our char set. Then we're going to shift it by 32. So that matches this exactly. LCG times the length, which is going to be our range, and then shifted by 32 bytes. And then let's increment our loop condition here, and we'll return key. So if everything goes right, let's go ahead and do a keygen for the seed of 0. Save that. Open the command line. Keygen. And nothing happened. That is because I did not print. Try that again. Okay, let's compare that string to what we got in the debugger. ABSKO, blah, blah, blah. All right, cool. SBKI, blah, 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 blah. So, looks like we've recreated that keygen. Now, it's usually a good idea to test this with a couple different seeds just to make sure we didn't get lucky with just the generation here. So, let's go ahead and let's restart that. And let's try pushing some other seeds. So, let's go to our seeding function. And we're going to go to move that to there. You know what? I killed the command of where I actually give it a variable. So I'm actually not sure how to get that again. Okay, let's go ahead and open our original. Oops. It's because I destroyed those references. My breakpoints still here? They are. All right, let's go ahead and let it generate its own seed and then just watch what it is, I guess. So we're gonna go to here. We're gonna follow this address. We'll see it's 0 right now, but now we have this value. So let's copy. That is bytes. And let's go ahead and keygen this. So this is hex. And this may actually be little endian. Yeah. Let's actually copy this version of it. If I'm wrong, I'll just flip the bytes. Keygen, so let's try it with that. So we should see this HFSS if we're correct in this. Let's go ahead and jump, and there we go. We have the same value here. So, all right. So that was a quick little tearing apart of a keygen with a ransomware. LCGs are pretty common for several different languages. We'll see from this chart, there's a Borland C/C++ version that uses these constants. So that'd be if it was compiled with just plain C using srand and rand. We'll also see an explanation here about the output, that goofiness with where we had to do it times the length and then bit shift it. We'll see that is right here. It's the seed times the length. So seed times the length, and then we take 32 bytes of it because it's the upper bits of it. So that's what this this column kind of means. And then we can also see there's the C++ version. This would be like more common in my experience. Just, you know, if you make a C++ program using srand and rand, it uses these constants. Apparently there's a different variant of that one. I haven't really run into any of the other ones here, except for I think I saw a Pascal one once. Actually, oh, I'm sorry. Pascal and Delphi use the same here. So it's a pretty simple algorithm to spot once you've seen it at least once or twice. At least just seeing this little block here, just seeing that this number changes, and there might be an addition instead of increment, since other ones use a different number than just one. So that's been a quick analysis of a keygen with a ransomware, and this would be something that we could easily generate all the possible keys, just guess them all, recreate these keys, and then guess against the encryption algorithm. So I'll leave a simplified version of this script up on GitHub or something. And if you have any questions, feel free to leave a comment. Until next time, thank you for watching.